Friction, part 2. What is friction? A force of resist motion involves objects that are in contact with each other. There has to be contact. As I was saying, it's not well understood. Some cause of friction, then an object deforms a surface and vice versa, so it creates this little hole type of thing, and the plowing force is required to move the object over these deformations or these holes. It has to sort of go uphill. Other scientists believe that irregularities interlock. When I say irregularities, I mean that the surface itself isn't perfectly smooth, and they offer resistance to move. So they sort of hook in each other, right? Like Velcro almost. We talked about starting friction, which is the maximum frictional force between stationary objects. It's also referred to as static friction. It is the biggest frictional force. And once you get an object moving, then that's known as sliding friction or kinetic friction, and it is the frictional force between objects that are sliding with respect to each other. Okay, so some properties of friction. Characteristics of friction. Key one here, friction acts parallel to the surfaces that are in contact. Parallel. Everyone know what parallel means? I hope, about grade 7 or 8, right? In the same direction. So like, for example, if you've got a ramp and the object is sliding down the ramp, which way is friction? It's up like that, right? It's parallel to the surface. And it's in the direction opposite to the motion of the object or to the net force tending to produce such motion. It's always opposite the motion. What's the second property of friction? Well, it depends on the nature of the materials in contact and on the smoothness of the surfaces. I think you all know that the smoother two surfaces are, the more or less friction out. The smoother the surfaces are. Would there be more friction or less friction? Usually less. Up to a point. Although they found that when objects are incredibly smooth, what happens is the molecules get so close together and there's sort of an electromagnetic pull between them and it actually increases friction. It also creates sort of a vacuum effect as well. But generally in everyday life, the smoother the surfaces are, the less the friction. Friction only depends upon the smoothness and the nature of the materials. Do you have to have two surfaces to figure out how much friction there is? Like if I've got a smooth tabletop, but I've got like I don't know, like a curling slider on a tabletop, right? How much friction would there be? Not a whole lot, but if you put that curling slider on ice, there's going to be even less friction, right? So there always has to be two. Sliding friction is less than or equal to starting friction, because starting friction again was the maximum. So it's always easier to push something once it's moving. Here's one that's kind of contentious or controversial. Friction is practically independent of the area of contact. Now I usually go get a textbook when I do this. Is the front of this textbook the same material as the side of the textbook? More or less, right? So where is there more friction? When I have it flat like this, or if I were to put it on its spine like this? Where is there more friction? The answer is it's the same amount of friction, because friction only depends on what? The nature of the depends on the nature of the materials in contact and the smoothness of the surfaces. If this front of the book is the same as the spine of the book, then the amount of friction is the same. What's different is the pressure. We all know that if you're on thin ice, what should you do? Sort of spread yourself out, right, to reduce pressure. That's not what we're talking about here. People think that the small tires are less friction. Okay? It's whether it's small or thick, it's the nature of the rubber that matters. It's the heat that's generated that's different. So friction is practically independent of the area of contact. In most situations. And starting or sliding friction is directly proportional to the force pressing the two surfaces together. And I'm going to draw a picture here. Free body diagram. What is the force that causes those two objects to be pushed together? Gravity, which is the weight force. And that weight force is dependent upon what? The mass. How big the object is. Pause for a second. Go back to my book example. Does the book weigh the same when it's sitting flat like this as it does when it's on its spine like this, Brayden? Does the book weigh the same? You can tell me. Oh. Does the book weigh the same?
Yeah.
Same book, same mass, right? Weighs the same, right? So the force between them is the same, whether it's like this or whether it's like this. Okay? And the bigger that force, if I put a 1 kilogram mass on top of the book, more force, more friction, right? I think that's it. Is there anything else in the handout there that's important? Did you see? I went through all the 5 on the right there, I think, right? Oh, I know. There's one more. We got to do the formula. Like, how are we going to solve these problems? Here it is here. Here's the formula. Just give me the formula, Mr. Bennett. It's called the coefficient of sliding friction. And it is, you probably should, if you're not writing anything down, at the very least, please highlight that on your handout, right there. Okay? It's called the coefficient of sliding friction. It is the ratio of the force of friction to the normal force. And this funny looking Greek letter right here is the Greek letter mu, M-U. Mu. It looks like a U, but it's got a tail on the front. And it's pronounced mu. I think it's the Greek M. Weirdly enough, when we were in Greece a few years ago, I could read words, like I knew most of the letters, but I had no idea what they meant. Kind of weird being able to do that. I could actually spell it, but I didn't know what it was. Okay, so mu is equal to FF over Fn. That's going to be your new friend for the next couple days. Shall we jump right into the examples? I think you already have these, so I'm going to relieve you from writing out the questions. So you should have this page that has 3 examples on it. Should you do these, do you think? Again, it's up to you. If you think you learn better by just watching and then you want to print them out later, you go right ahead. Whatever works best for you. Okay, so we got 3 examples. They are ranged from relatively easy to a little bit more challenging. Okay, they'll take us about 15 minutes to go through, maybe less. Example number 1, a box with a mass of 175 kilograms is pulled along a level floor with a constant velocity. Is that important, the word constant velocity? Oh yeah, because when you see that, it's telling you something, and it's something that's good. Tyler, you can put the phone away, you need to pay attention. Mom's got to work, can't talk. If the coefficient of friction between the box and the floor is 0.34, what horizontal force is exerted in pulling the box? We are looking for what horizontal force? What are we solving for? We're solving for an applied force. What do we know? We know mu is 0.34. We know the mass is 175. We know G is minus 9.8. Let's draw a diagram. We got weight force. We've got normal force. We've got an applied force. Oh, I think I might have made a mistake. Constant velocity, what does that mean? No acceleration. So it means that my applied force is the same as the friction force. So, I mean, the only mistake I made was probably drawing that too big, right? I can solve that by doing what? Making my friction force equally as big, right? Applied force and friction force are balanced. Okay, what am I trying to solve for? What horizontal force? I'm solving for FA. That's what I'm solving for. How am I going to get that? Well, if I can find the friction force, then I can make them equal to each other. How do I get the friction force? Well, our new friend is mu equals FF over Fn. I know the mu. Do I know the Fn? I don't know the Fn. How can I find Fn? It's equal to Fw. Can I find Fw? I got mass and gravity. There's our roadmap. There's our plan. I worked backwards to get to there. It is almost always a good idea to start every question. I can't think of one where you don't need to know the weight force if it's not given. Fw is equal to mg. If you're not sure, start with that. And likely you're going to get at least 1 mark for that. 175 times minus 9.8. I get 1715 minus 1715. 175, the mass, times minus 9.8, minus 1715. So if the weight force is down, minus 1715, then that means that my normal force, which is up, is going to be 1715. Now, after a little bit of practice and whatnot, you will get to the point where you just, you don't even have to show that. We just sort of assume everyone knows how to do that. So the normal force is 1715. And now I'm going to use our new friend, mu equals FF over Fn. And our mu value was 0.34. We're going to solve for friction force over normal force of 17. Oops. And again, this last little bit here, that should be involuntary math. You should know how to do that. How do I solve that? We're going to multiply, right? And everyone likes the unknown being on the left, so I'm going to take 0.34 times 1715, and I'm going to get, can't read my own writing, 583.1. That's a lot of friction. And we've already determined that the applied force is equal to friction force. How come? Because it's moving at a constant velocity. So therefore, you guys know the 3 dots in a triangle? Have I talked about that? 3 dots in a triangle means therefore, or in conclusion. Therefore, your applied force is 583.1. How hard was that? Really, it's really only what? It's really only 2 steps. What would make a question like that harder? What if it's not moving at a constant velocity? Would that make it harder? Yeah. Everybody good with this one? Any questions you want to ask about that? All good? This time we have a box with a mass of 100 kilograms. It's accelerated by a force of 200 newtons across a level floor. If the coefficient of friction between the box and the floor is 0.2, what is the overall acceleration? Is it moving at a constant velocity? No. It is accelerated. Is the picture more or less the same? Yep. This time our applied force is bigger. What did I suggest the first step should be? Find the weight force. Let's do that. Technically it's minus, so that's going to be minus 980. 200 times minus 9.8 is minus 980. And if the weight force is minus 980, then that means that our normal force Fn is positive 980. What should I do next? I didn't sort of make a plan, did I? A roadmap. I just sort of jumped in. What are we trying to find? We're trying to find acceleration. What's going to be the last formula that I'm going to use to find acceleration? I got the mass. I'm trying to find the acceleration. F net equals ma. Do I know the net force? No. How am I going to get the net force? It's going to be Fa and Ff added together, right? Do I know the Fa? I do. It's 200. It's right there. I didn't do that, did I, at the start? My Fa is 200. I need to know my friction force. So I'm going to use our new friend again. Ff over Fn. By the way, you're going to use this over and over and over again. Even into grade 12, we use it lots. .2. We're going to solve for friction force. Normal force is 980 newtons, giving us a friction force of 196. There's 196 newtons of friction. Multiply 980 times 0.2. So what's our net force? Oh, messed up. Applied force was 200 minus 196. We only have 4 newtons of net force. But that's not what we want. We want the overall acceleration. One last thing to do. Four is equal to, what was the mass? 100. How do you solve that? Divide both sides by 100. A equals 0.04 meters per second squared. Is that one harder? Absolutely. Is there more steps? Absolutely. 1, 2, 3, 4 steps. That's sort of, medium. Okay, I'm going to give you 2 minutes to read the next one and sort of look ahead and do some pre-thinking while I go do attendance. Okay, last one of the day. A box with a mass of 46 kilos is pulled along a level floor, constant speed. Highlight that, underline that, that's important. What does constant speed mean, Reese? Yeah, but what does it mean in terms of forces? What's the same? What do you mean by the, what do you mean by the same? Okay. The forces are, the word I'm looking for is the forces are balanced, right? The net force is 0. That's what it means. By a rope that makes an angle of 30 degrees with the floor as shown. If the force in the rope is 260 newtons, what is the horizontal component? What is the normal force, and what is the coefficient of sliding friction? Is this one harder? Yeah, it is. This one's considerably harder, and it's about as hard as they're going to get. What makes it hard is that the force is up here at an angle. Let me just do this for the time being. Do you guys have that picture? Do you have the picture? No? Okay. So if my arrow here is at 30 degrees, is all of that 260 degree or 260 newtons going into pulling it sideways? If it's at an angle? Does all of 260 pull sideways, Alex? Alex is shaking his head. He's saying no. I'll ask it a different way. What if I were to increase the angle like this? Would it go as hard or as fast with the right? No, I think you guys know that. And if I made it even steeper, then, I mean, if I made it like that, it wouldn't go sideways at all, would it? So the angle matters. If I made it less, if I only made it like, say, 10 degrees or 5, it would go pretty much the same as if it was perfectly flat, right? So yes, the angle matters. So then the question is, how much of it pulls it sideways? Well, that, and I think we've talked about this already, is the horizontal component, right? Which I am now calling, not FH anymore, I'm now calling it FAX. The X component of the applied force. It's a portion of that applied force. Now, that means, and maybe some of you have sort of thought about this a little bit, it means that there's another component as well. What would I label it? FAY. The Y component of the applied force. And components are big in grade 12. We do all our vectors by components. So this is sort of the intro to that. What do you think the FAY, if the FAX is what's pulling it sideways, what does the FAY do? Lifting it up. And what does that do to the friction force, do you think, Hannah? Is it going to change it? Is it going to make it less, or is it going to make it more? More? Less. More. Well, think about experience, right? If you've got a great big heavy box or a couch or something, you're trying to slide it across the carpet floor, what would, if you lift it a little bit, is it easier or harder to push? It's easier, right? So in fact, this FAY actually is going to reduce friction. Okay. So, what is the horizontal component FH? What is the normal force? And what is the coefficient of sliding friction? Let's go. Now, I've already given you this weight force. Where did it come from? It's not always going to be given. Let's just do that. FW is equal to mg. It was 46 times minus 9.8 is minus 450.8, meaning that the normal force then is 450.8. Oh, hold on. Is the normal force 450.8? If I put an arrow that's the same length as this one, did I get close? Yeah, pretty close. If I do this, and there's this FAY, then what about the total forces up and down? Are they balanced? They're not, right? Because now I got this one up and down with that one, and now the up and down is greater than the down, which means the object's going to be accelerating upward. Well, that doesn't happen. So what this means is that this normal force here, whoopsie, is actually, come on, it's actually what? It's smaller. In fact, this normal force right here, Fn, and the FAY, in fact, add up to what? To this 450.8. Okay? So the FAY, the Y, I know this is confusing, I get it. I can see the deer in the headlights look on their faces, I see it. Don't worry, we're going to come back to it. I'm going to repeat. Okay? I'll re-explain, don't worry. The FAY does what? It reduces the amount of normal force, and that's what we want because it's going to reduce the friction. Okay, so let me show you here. That was the explanation. So I'm going to get rid of this. Okay, we've got our horizontal component. That's part A. It then asks for what is the normal force. The normal, the up, the net force up, has to equal the sum, my Fn plus my FAY have to be equal to how much? This 450.8. The total of the up has to equal the total of the down. What are the ups? Fn and the FAY. Those are my forces up, and my down is my FW, is my 450.8. Okay, I'm getting close to done, don't worry. It would be. It would be. But would this number be equal to minus 450.8, or would it be equal to, because this is the sum of the ups, right? So we have to flip it. We have to change it because the 450 has to be up. The sum of these two has to add up to 450.8 to balance. Another way that I've written it before, and I regretted, as soon as I wrote that down, I went, oh, I screwed up. This is a better way to write it. Good question, Megan. What's the net Y forces add up to? 0, right? And what is the net Y's? Fn plus Fay plus Fw must equal 0. Fn, the normal force, plus the Y component, plus the weight force have to add up to 0, which means Fn plus Fay, and this is then minus 450.8, and when it goes to the other side, it becomes positive. Does that make you better? Yeah? Are you just saying that to make me feel better? No? Do we know our Fay? We haven't solved it yet, have we? How can I get it? How can I get this Y component? Think back to grade 9. It's opposite, right? Opposite. So we got our angle, we got our hypotenuse. So it's going to be sine. Sine theta is opposite over hypotenuse. Sine 30, yeah, lots to do. Sine 30 is opposite. How many times do you think I've done this question? A lot of years. Probably 30 times in front of classes, at least. Sine 30, opposite is what I'm solving for, Fay. What's the hypotenuse of my triangle? 260. Which means that my Fay is going to be 260 times the sine of 30. 130 newtons. Hey, you know what? I realized I said that we did it, but I lied. We didn't, right? Did we actually find the horizontal component? I don't think we ever did we? We never did find the FH or the FAX. How am I going to do that? It's the same as this, right? It's going to be cosine, though. Cosine 30 is equal to adjacent FAX. I hear people thinking, how am I ever going to be able to do this on my own? You're going to have to. It's going to take practice. What are you talking about? This has been on the test since the beginning of time. Countless students have gotten through this, Josh. Countless will after you. It's not that hard. It just takes some practice. $225.2. You can do this. It's going to take practice. So what I've done is I've broken this down into X and Y. We call these components. So this is really part A. 225.2. 225.2, that's going to be newtons. These are all forces. Okay. What is the normal force? Let's go back to this step right here. Right? Well, this is part A right here. This is part A, and all of this other stuff, I sort of jumped ahead a little bit here. Right? All of this is part B. So I'm going to take this FAY, this 130 is going to go where? It's going to go in there. Fn plus Fay, I'll write it out for you here. I'm going to write out that statement again, and then I'm going to take this 130, and I'm going to put it in there. And I get a normal force of, when these goes to the other side, it becomes 450.8, which was my original weight force. Subtract the 130, 320.8 newtons. You can do this, you guys. Yes, you can. It takes practice. I have reduced the normal force. How did I do it? The normal force should have been how much? 450.8. How did I reduce it? By applying a force up. Right? How could I make it less? Well, if I took this angle and did what? If I increase the angle, right? It would increase that y component. Okay, so that's my normal force. Part C. What is the coefficient of sliding friction? Hang with me here. About 2 more minutes. Run out of space? Don't write it down yet. Pens down. Pens down. Mu equals FF over Fn. Do I have the normal force? Yes. I'm looking for the coefficient of friction, the mu value, right? I'm looking for mu. Do I have the friction force? I don't. I don't have friction. But you'll remember way back at the start, I highlighted this. Is that important? Constant speed. Because what does that mean? It means the forces are equal or balanced. So what balances the FF? Key part here, key point. Watch, watch, watch. What balances the FF? The FAX, exactly. The FAX, the horizontal component, which is sideways, is balanced by the friction force. So the reason I said don't write it down is because I'm going to put that over there, and I'm going to say, you can write this down now, that the FF is balanced by the FAX, which is 222.5. 225.2. Right? So now, mu equals 225.2, normal force 320.8, and you get a mu value of about 0.7. I'll pause there for a second, let you soak that all in. Renee, I think, is asking, shouldn't the friction force be negative? That's what you're saying? Yes, and you're absolutely right. Generally, we don't care about that in this particular formula because this is a ratio of forces over forces. So, and because the friction force is sort of left to right, there's an X, and the normal force is up and down. So the negativeness, the direction really doesn't make sense kind of thing. So we sort of ignore it, and mu values are always stated as positive. So yes, you're right. It's just sort of common to not do it. You will find that these mu values are almost always less than 1. Excuse me, less than 1. A little choked up there for a second. Almost always less than 1. If you get a mu value of 17, good chance you've done something wrong. One last thing before I turn you loose. What is the unit for mu? What do you think? What are the units for friction force? Newtons. What are the units for normal force? Newtons. What happens when you got newtons over newtons? Nope, they cancel out. And the unit is nothing. This is the one time that you should not have a unit. No units. Because it's newtons over newtons. Okay, you guys have done really well. I could sense the sort of, oh my God, right, on that example 3. I get that. Okay, it's going to take practice. Okay, we got a little bit of time. There are some, I'm going to more will because I can find a way already. Give me 30 more seconds. You've got a little bit, there's some problems here you can work on. Shelby, 30 more seconds, please. You've got some problems here you can work on. You've got some problems here you can work on. Okay? Try one or two while the knowledge is fresh in your brain. I'm done.